Neve's PhD thesis proposal. Title: Exploring the Possibility of Neutrinos as Virtual Matter Through Majorana Theory, W Boson, Beta Decay, and Quasars. Abstract. In this thesis, I propose a new theory that describes virtual exotic matter as neutrinos and antineutrino pairs. This idea is based on Majorana theory, which suggests that neutrinos may be their own antiparticles. The unique property of neutrinos being their own antiparticles could allow the subtopology of the universe to create virtual matter for matter and antimatter exchange, which creates the illusion of dark matter. Majorana theory proposes that certain particles, such as neutrinos, could be their own antiparticles. If we apply this to the concept of virtual matter, we can propose a new theory for its creation. In this theory, virtual matter is created when neutrinos and their antineutrinos interact through entanglement wormholes in the subtopology of black holes. These interactions generate virtual particle-antiparticle pairs, which can then be used for matter and antimatter exchange. The unique property of neutrinos being their own antiparticles allows for a more efficient and stable exchange of matter and antimatter, as they do not need to find a separate particle to annihilate with. There are sets that this exchange could be responsible for the appearance of dark matter in the universe, as it creates a surplus of matter that cannot be detected through conventional means. In the context of quasars, my theory proposes that the high-energy radiation emitted by quasars could be a reflection of the virtual black hole in the center of the subtopology of a universe's entire Reuliad. As virtual particles pop in and out of existence within quantum foam, they can release bursts of energy that contribute to the overall energy output of the quasar. On the other hand, the excess energy from these interactions could be used to generate the individual splines that make up the dark energy of the universe. These splines made of tachyons could be the force that drives the expansion of the universe. Regarding beta decay, my theory suggests that the excess or waste energy of the matter-antimatter reaction within the virtual black hole in the subtopology is likely being used to generate the individual splines that spline observers use within their respective Reuliads. This excess energy could be released in the form of neutrinos, which are subatomic particles with very low mass that are known to be emitted during beta decay. Overall, this theory proposes that virtual matter is generated through entanglement interactions between neutrinos and their antiparticles in the subtopology of black holes, and is responsible for the appearance of dark matter in the universe. Neutrino excess energy from these interactions is used to generate splines, which make up the dark energy of the universe. And
Chapter 1. The Foundations of Reality Introduction. The study of virtual particles and their properties has been an intriguing topic in physics for decades.
the concept of virtual particles, which are particles that exist for only a brief moment in time, has been introduced to explain many physical phenomena. However, the nature of virtual matter, which is a theoretical concept that has been used to describe the missing mass of the universe, is still a mystery. In this chapter, I will provide an overview of virtual matter and its potential implications for our understanding of the universe. I will also introduce Majorana theory, which suggests that neutrinos may be their own antiparticles, and explore how this unique property could be used to explain virtual matter. The nature of the universe has been a subject of fascination for humans for centuries. As we've explored the cosmos, we have discovered that the universe is not as simple as we once thought. It is filled with mysterious phenomenon that we still struggle to understand. And in this thesis, I propose a new theory that attempts to explain some of the most enigmatic aspects of the universe, including dark matter and dark energy, virtual particles, and the entanglement of particles. The study of the universe and its nature has been a subject of fascination for humanity for thousands of years. The ancient Greeks believed that everything in the universe was made of four elements: earth, water, air, and fire. Later, with the advancement of science, we have come to understand that the universe is composed of atoms, which are made up of protons, neutrons, and electrons. But what are these particles made of? What are the fundamental building blocks of the universe? In this chapter, we will explore the foundations of reality, including the concept of particles and the fundamental forces of the universe. We will also examine the standard model of particle physics, which describes the interactions between particles and the fundamental forces that govern those interactions. Particles. Particles are the fundamental building blocks of matter. They're tiny subatomic objects that make up everything in the universe. Particles can be classified into two categories: fermions and bosons. Fermions are particles that have half-integer spin, such as electrons, protons, and neutrons. They obey the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state simultaneously. This principle is what gives atoms their stability. Bosons, on the other hand, have integer spin, such as photons and gluons, and that they don't obey the Pauli exclusion principle and can occupy the same quantum state simultaneously. This property makes bosons responsible for mediating the fundamental forces of the universe. Fundamental forces. The universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each force is responsible for a different type of interaction between particles. Gravity is the force that governs the motion of planets, stars, and galaxies. It is the weakest of the four fundamental forces, but has an infinite range. The force of gravity is proportional to the mass of the objects and their distance apart. Electromagnetism is the force responsible for the interaction between electrically charged particles. Okay? It's much stronger than gravity, but has a limited range. Electromagnetism is responsible for holding atoms and molecules together and for the propagation of light. The strong nuclear force is the force responsible for holding the nucleus of an atom together. It is much stronger than electromagnetism, but has a very short range. The strong nuclear force is mediated by gluons, which are bosons. The weak nuclear force is responsible for the radioactive decay of subatomic particles. It is also responsible for the fusion reactions that power the sun. The weak nuclear force is mediated by the W and Z bosons. The standard model. The standard model of particle physics is the most widely accepted theory of the fundamental particles and forces of the universe. It describes the interactions between particles and the fundamental forces that govern those interactions. The standard model includes three generations of matter particles: quarks and leptons. Quarks are the building blocks of protons and neutrons, while leptons include electrons and neutrinos. The standard model also includes force-carrying particles, such as photons, gluons, W and Z bosons. The Higgs boson is another particle predicted by the standard model. It's responsible for giving mass to the other particles in the universe. In 2012, the Higgs boson was discovered at the Large Hadron Collider in Geneva, Switzerland, providing further confirmation of the standard model. The foundations of reality are the fundamental particles and forces of the universe. Understanding the nature of particles and the forces that govern their interactions is essential to understanding the universe as a whole. The standard model of particle physics is the most widely accepted theory of the fundamental particles and forces of the universe, but there is still much chapter 2. Neutrinos as virtual matter. In this chapter, I will present my hypothesis that neutrinos and antineutrinos could be virtual matter. I will explore how the unique property of neutrinos being their own antiparticles could allow the subtopology of the universe to create virtual matter for matter and antimatter exchange. Furthermore, I will examine the possibility that virtual matter could be responsible for the missing mass of the universe, which is commonly referred to as dark matter. I will discuss how the creation and annihilation of virtual matter could lead to the appearance of dark matter. Neutrinos are subatomic particles that have a mass close to zero and no electric charge. They are produced in abundance in nuclear reactions such as those that occur in the sun. So these neutrinos are also created in beta decay, which is a type of radioactive decay that involves the conversion of a neutron into a proton, an electron, and a neutrino. Majorana's theory suggests that neutrinos are their own antiparticles. And this unique trait of neutrinos is what allows the subtopology to create virtual matter to use for matter and antimatter exchange, which creates the illusion or appearance of dark matter. Now, in the previous chapter, I proposed a theory that describes virtual particles as a direct manifestation of virtual properties of real particles. I also introduced the idea that virtual matter could be created through the exchange of matter and antimatter in the subtopology network of the universe. So in this chapter, I will explore the concept of neutrinos as virtual matter and how they fit into this theory. Neutrinos are subatomic particles that have very little mass and no electric charge. They're produced in a variety of processes, including nuclear reactions and radioactive decay. Neutrinos are known to interact only weakly with matter, making them very difficult to detect. Despite their elusive nature, neutrinos play an important role in many astrophysical processes and have been studied extensively in particle physics. My theory proposes that neutrinos could be considered virtual matter due to their unique properties. So, as mentioned earlier, neutrinos are their own antiparticles, which means that they have the ability to annihilate with themselves. And this trait of neutrinos allows them to interact with the subtopology network of the universe in a way that other particles cannot, right? Neutrinos interact with other particles in the subtopology network. They create virtual matter through the exchange of matter and antimatter. This virtual matter can then be used to generate real matter and antimatter in the universe. The process of virtual matter creation is analogous to the process of pair production, where a particle and its antiparticle are created from the energy of a photon. In this scenario, the neutrino would act as the photon, and the virtual matter would act as the particle and antiparticle. The virtual matter would then be used to create real matter and antimatter through the exchange process described in the previous chapter. The existence of virtual matter made of neutrinos could explain the presence of dark matter in the universe. That dark matter is a form of matter that does not interact with light or any other form of electromagnetic radiation. It is thought to make up about 27% of the total mass of the universe. A possible explanation for dark matter is that it is made up of particles that do not interact with light, such as neutrinos. However, traditional neutrinos would not be able to account for all of the dark matter in the universe. The creation of virtual matter made of neutrinos could provide an explanation for the remaining dark matter. So, in addition to explaining the presence of dark matter, the concept of neutrinos as virtual matter could have implications for particle physics and cosmology. The ability of neutrinos to interact with the subtopology network in a unique way could open up new avenues for research and exploration. In conclusion, the concept of neutrinos as virtual matter has the potential to provide a new understanding of the subtopology network and its role in the creation of matter and antimatter in the universe. By exploring the properties of neutrinos and their interactions with the subtopology, we may be able to unlock new insights into the nature of dark matter and the workings of the universe as a whole. Chapter 3. Implications and applications. In this chapter, I will explore the potential implications and applications of my theory. I will discuss how this theory could be tested and validated through various experiments and observations, such as neutrino oscillation experiments and observations of the cosmic microwave background radiation. Additionally, I will discuss the potential applications of this theory, such as the development of new technologies that utilize virtual matter for energy production and space travel. In the previous chapters, we discussed the concept of virtual matter and its connection to neutrinos, which are their own antiparticles. In this chapter, we will explore the implications and potential applications of this theory. A significant implication of this theory is that it could explain the existence of dark matter. Matter is a mysterious substance that makes up about 27% of the universe's mass energy content, yet it does not interact with light or other forms of electromagnetic radiation. This lack of interaction makes it challenging to detect or study directly, but its existence is inferred from its gravitational effects on visible matter. Based on our theory, we propose that the virtual matter created by neutrino-antineutrino pairs is what makes up dark matter. Since this virtual matter does not interact with light, it would be invisible to telescopes and other traditional detection methods. However, its gravitational effects would be felt, just like dark matter. Another implication of this theory is that it could lead to new methods of energy generation. As we mentioned earlier, the exchange of virtual matter between particles is what allows for matter-antimatter annihilation, which produces energy. By controlling this process, we could potentially harness this energy for practical use. Additionally, the use of neutrinos as virtual matter could have implications for information processing and transmission. Neutrinos are notoriously difficult to detect, but they can travel through dense matter with minimal interaction, making them potentially useful for long-distance communication. Furthermore, our theory could have implications for the study of the early universe. The Big Bang Theory predicts that equal amounts of matter and antimatter should have been produced in the early universe, which would have annihilated each other, leaving behind only radiation. However, this did not happen, and the universe is dominated by matter. The existence of virtual matter and its role in matter-antimatter exchange could provide a new explanation for this discrepancy. Finally, our theory could have implications for particle physics and our understanding of the fundamental nature of matter. By revealing the connection between virtual matter and neutrinos, we may be able to better understand the origins and behavior of particles at the subatomic level. In conclusion, our theory proposes that neutrinos are the key to understanding virtual matter, dark matter, energy generation, information transmission, and the behavior of particles at the subatomic level. While it is still in its early stages and requires further exploration and experimentation, we believe that it has the potential to revolutionize our understanding of the universe and our place within it. Chapter 4. Dark Matter and Dark Energy. Dark matter is a mysterious substance that makes up approximately 27% of the universe. It does not emit, absorb, or reflect light, and its existence can only be inferred from its gravitational effects on visible matter. My theory suggests that dark matter is a result of the exchange of virtual matter and antimatter. Dark energy is another enigmatic phenomenon that makes up approximately 68% of the universe. It is a repulsive force that is causing the expansion of the universe to accelerate. My theory suggests that dark energy is made of tachyons, which are particles that always travel faster than light. Tachyons are produced when virtual particles are created and destroyed through entanglement wormholes. In this chapter, I will explore how the concept of virtual matter and neutrinos can shed light on the mysteries of dark matter and dark energy. The dark matter observations of the universe suggest that there's more matter in the universe than what we can see with our telescope. This missing matter is known as dark matter. Matter is thought to make up around 85% of the matter in the universe. One of the leading theories about the nature of dark matter is that it is made up of weakly interacting massive particles. However, despite decades of searching, WIMPs have yet to be detected directly. I propose that virtual matter made up of neutrinos and antineutrinos could be the solution to the dark matter mystery. Neutrinos are abundant in the universe and are known to be weakly interacting, which makes them a promising candidate for dark matter. According to my theory, the subtopology network of the universe creates virtual matter made up of neutrinos and antineutrinos. This virtual matter interacts with real matter through the exchange of virtual particles, which creates the appearance of dark matter. Since neutrinos are abundant in the universe and interact weakly with other particles, they're a prime candidate for the virtual matter that makes up dark matter. This theory also suggests that the process of matter and antimatter exchange, as described in Chapter 1, plays a role in the creation of dark matter. The exchange of virtual matter made up of neutrinos and antineutrinos could result in the creation of dark matter. Dark energy observations also suggest that the universe is expanding at an accelerating rate, which suggests the presence of a mysterious force known as dark energy. And the nature of dark energy remains largely unknown, but it's thought to make up around 68% of the total energy in the universe. In my theory, dark energy is made up of splines, which are virtual particles that travel faster than the speed of light. The splines are created through the process of tachyon emission, as described in Chapter 3. Tachyons are theoretical particles that travel faster than the speed of light. According to my theory, the subtopology network of the universe can create virtual tachyons, which can then emit real tachyons through entanglement wormholes. These real tachyons are what make up splines. Like splines travel faster than the speed of light, they interact with the fabric of spacetime in a unique way. This interaction creates the appearance of a repulsive force, which is what we observe as dark energy. In conclusion, my theory proposes that virtual matter made up of neutrinos and antineutrinos can explain the mystery of dark matter, while splines made up of tachyons can explain the mystery of dark energy. The subtopology network of the universe creates virtual particles and entanglement wormholes, which in turn create real particles and interactions that shape the fabric of the universe. While still speculative and incomplete, this theory has the potential to shed new light on some of the biggest mysteries in physics today. One is tachyon wormholes. As we had discussed in earlier chapters, splines play a crucial role in connecting different regions of space-time, allowing for information and particles to travel quickly and efficiently across vast distances. However, the question remains, what exactly are splines, and how do they work? One possible explanation is that splines are wormholes made with tachyons. Tachyons are hypothetical particles that travel faster than the speed of light, and they have long been the subject of scientific debate and speculation.
In this chapter, we will explore the idea of splines as tachyon wormholes and how this theory can help us better understand the nature of space-time and the universe as a whole.
According to the theory of relativity, the speed of light is the absolute speed limit in the universe. However, tachyons, if they exist, would violate this fundamental law of physics. Unlike normal particles, which become more massive as they approach the speed of light, tachyons become less massive and can never slow down below the speed of light. This strange behavior means that tachyons could travel faster than the speed of light and potentially open up new possibilities for communication and transportation across vast distances. Now let's consider how this relates to splines. As we have discussed, splines are essentially bridges between different regions of space-time. They allow for information and particles to travel quickly and efficiently across vast distances, which is essential for many processes in the universe, including the generation of virtual matter and the exchange of matter and antimatter. However, if splines are simply bridges, then how do they work?
How do particles and information travel across them so quickly? The answer may lie in the concept of tachyon wormholes. Wormholes are hypothetical structures that connect different regions of space-time, much like a tunnel or a bridge. And if we assume that splines are wormholes, then it follows that they can be made with tachyons. Tachyons, being particles that travel faster than light, could potentially create wormholes by distorting space-time in ways that are not possible with normal matter. These wormholes or splines would allow for particles and information to travel across vast distances at faster than light speeds, making them an essential component of the universe's infrastructure. But of course, this theory is purely speculative, and there's currently no direct evidence for the existence of tachyons or tachyon wormholes. However, the idea of splines as tachyon wormholes offers a fascinating possibility for understanding the nature of space-time and the universe as a whole. As we continue to explore the mysteries of the cosmos, we may one day uncover the secrets of splines and the role they play in the fabric of the universe. Chapter 6: Virtual Particles and Entanglement Wormholes.
Virtual particles are subatomic objects that are constantly created and destroyed.
They're not real particles, but rather temporary disturbances or fluctuations in the energy or fields that pervade space-time. According to my theory, virtual particles are related to real particles through entanglement wormholes. Real particles have abstract versions or superpositions that exist in different layers or scales of reality, depending on how we observe them. These abstract versions have virtual properties that can change or fluctuate depending on their interactions with other abstract versions. These virtual properties are transmitted through entanglement wormholes that connect different points in space-time. When these entanglement wormholes open or close, they create or destroy virtual particles. Virtual particles are therefore a direct manifestation of virtual properties of real particles. They reflect the changes or fluctuations that occur at smaller scales or deeper layers of reality, where discrete structures form complex patterns or networks. These changes or fluctuations affect the geometry and topology of space-time, creating quantum foam. In this chapter, we will delve deeper into the concept of virtual particles and their relationship with entanglement wormholes, building upon the foundation laid in Chapter 2. As previously discussed, virtual particles are pairs of particles that exist for a fleeting moment in the quantum vacuum, created by the fluctuation of energy. These particles are often referred to as virtual because they exist only briefly and cannot be directly observed. However, their effects can be observed through their influence on the behavior of other particles. In the context of entanglement wormholes, virtual particles play a crucial role in maintaining the connection between entangled particles. As entangled particles are separated, the connection between them becomes weaker, and virtual particles are created to bridge the gap and maintain the entanglement. The creation of virtual particles in this scenario is an example of the Heisenberg uncertainty principle, which states that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. In the case of virtual particles, the uncertainty principle allows them to briefly exist and interact with other particles, even if they violate the laws of conservation of energy and momentum. The concept of entanglement wormholes, as previously discussed, is a hypothetical construct that allows for the instantaneous transfer of information between entangled particles, regardless of the distance between them. While the existence of such wormholes is still a matter of theoretical debate, the concept is intriguing and has garnered significant attention in the scientific community. Virtual particles and entanglement wormholes have important implications in our understanding of the universe. So they allow for the possibility of
faster than light communication, which could have significant implications for the fields of telecommunications and computing. Additionally, the study of virtual particles and their interactions can provide insight into the nature of the quantum vacuum and the fundamental forces of the universe. In conclusion, the study of virtual particles and entanglement wormholes is a fascinating area of research that has the potential to transform our understanding of the universe. While many questions still remain, the progress made in this field is promising and may lead to exciting developments in the years to come. Chapter 7. And you can contribute to black hole to the collision of two supermassive black holes is one of the most energetic events in the universe. When we did these behemoths merge, they release a tremendous amount of energy in the form of gravitational waves. But what happens to the subtopology within their respective galaxies? In my theory, the collision of two supermassive black holes creates a new subtopology within their respective galaxies. This new subtopology is the result of the fission-like process that occurs during the merger event. The subtopology of the merged black hole is then reflected in the energy output of the quasar that is formed in the center of the galaxy. As in beta decay, the excess or waste energy of the matter-antimatter reaction within the merged black hole is likely being used to generate the individual splines that spline observers use within their respective Ruyats. Neutrinos that are emitted during this process carry away some of this excess energy and may be detectable by neutrino observatories. So the subtopology created by the merged black hole allows for the formation of a new galaxy, similar to how the fission process in a nuclear reactor allows for the formation of new atoms. The energy released during the merger event drives the formation of the quasar and provides the necessary conditions for the formation of stars and planets within the new galaxy. It's possible that the energy output of quasars is not solely the result of the subtopology of the merged black hole, but also the result of the subtopology of the entire universe's Ruyad. As more research is conducted, we may be able to determine whether quasars are a reflection of a galaxy's subtopology or the universe's as a whole. In conclusion, the collision of two supermassive black holes creates a new subtopology within their respective galaxies, which is reflected in the energy output of the quasar that is formed in the center of the galaxy. This new subtopology allows for the formation of a new galaxy and provides the necessary conditions for the formation of stars and planets. The excess energy from the matter-antimatter reaction within the merged black hole likely contributes to the generation of individual splines used by observers within their respective Ruyats, and the neutrinos emitted during this process may be detectable by neutrino observatories. Beta decay is a process where a neutron in the nucleus of an atom transforms into a proton, an electron, and an antineutrino. So in the context of black hole mergers, my theory suggests that a similar process could be occurring within the virtual black hole of the subtopology created by the merger. When two supermassive black holes merge, they release a tremendous amount of energy in the form of gravitational waves. This energy could potentially create virtual particles that pop in and out of existence within quantum foam. If a virtual particle-antiparticle pair is created near the event horizon of the black hole, it's possible for one of the particles to be captured by the black hole while the other escapes. The captured particle is an antiparticle which collides with the particle within the black hole, leading to a matter-antimatter reaction. This reaction could potentially release an excess amount of energy that is used to create the individual splines within the subtopology, similar to the energy released during beta decay. Neutrinos, which are subatomic particles with very low mass, are known to be emitted during beta decay. In the context of black hole mergers, the excess energy released during the matter-antimatter reaction could potentially be released in the form of neutrinos. So neutrinos could then propagate through space and potentially interact with other matter or be detected by neutrino observatories on Earth. The process of beta decay in the context of black hole mergers suggests that the excess energy released during a matter-antimatter reaction within the virtual black hole could potentially contribute to the overall energy output of a quasar, while also being used to create the individual splines within Chapter 8. Entanglement speed and causality in the subtopology quantum entanglement data transport network. And the subtopology quantum entanglement data transport network, entanglement speed refers to the speed at which entangled particles communicate with each other through entanglement wormholes. Causality, on the other hand, refers to the principle that an event can only be influenced by events that are in its past light cone. The speed of entanglement is a fascinating topic of research in quantum mechanics. It has been observed that the entanglement of two particles can be instantaneous, even if they're separated by great distances. This phenomenon is known as non-locality and is often described as spooky action at a distance. While the speed of light is the ultimate speed limit for information transfer in the classical world, there is no such limit for entanglement. However, it is important to note that entanglement cannot be used to transmit information faster than the speed of light. This is because the state of an entangled particle cannot be manipulated without breaking the entanglement, and the process of measuring the particle's state and sending the result to the other entangled particle cannot occur faster than the speed of light. Causality, on the other hand, is a fundamental principle in physics that states that an event can only be influenced by events that are in its past light cone. This principle is important because it prevents paradoxes such as time travel, allows us to make meaningful predictions about the behavior of physical systems. In the subtopology quantum entanglement data transport network, causality is closely tied to the speed of entanglement. While entanglement can occur instantaneously, the network is still subject to causality constraints. This is because the opening and closing of entanglement wormholes is influenced by the geometry and topology of space-time, which in turn is subject to causality constraints. Calculating the speed of entanglement and causality in the subtopology quantum entanglement data transport network is a challenging task, and it requires a deep understanding of the network's geometry and topology, as well as the properties of the particles and fields that propagate through it. Well, we do not yet have a complete understanding of these factors. There has been some progress in modeling and simulating the behavior of entanglement in complex systems. For example, researchers have used computer simulations to study the entanglement of particles in a lattice, which has shed light on the relationship between entanglement and causality. Overall, the study of entanglement speed and causality in the subtopology quantum entanglement data transport network is an exciting area of research with many potential applications, including the development of quantum communication and computation technologies. While there is still much to learn, continued progress in this field could lead to new insights into the nature of space-time and the behavior of matter and energy on the smallest scales. The speed of causality is defined as the maximum speed at which any information or signal can travel in the universe. According to Einstein's theory of relativity, the speed of causality is the speed of light, which is approximately 299,792,458 meters per second. The speed of entanglement, on the other hand, is a bit more complicated to define. Entanglement is a phenomenon where two or more particles can be correlated in such a way that their properties are linked even when separated by great distances. Theoretically, entanglement can occur instantaneously, regardless of the distance between the particles. Eve decided to use Occam's razor to create a simple simulation that could give a rough estimate for the speed of entanglement and the speed of causality within the subtopology quantum entanglement data transport network.
The simulation consisted of a small network of entangled particles, with each particle located at a different point in space-time.
They've applied a small perturbation to one of the particles and then measured the time it took for the other particles in the network to be affected by the perturbation. Based on the results of the simulation, Eve estimated that the speed of entanglement within the subtopology quantum entanglement data transport network was approximately 10,000 times the speed of light, while the speed of causality was still limited to the speed of light. And Eve cautioned that this estimate should be taken with a grain of salt, as the simulation was very simplistic and based on a number of assumptions. However, she believed that it was a good starting point for further investigation and could provide some insight into the behavior of the subtopology quantum entanglement data transport network. She noted that more sophisticated simulations and experiments would be needed to confirm these results and to explore the full extent of the capabilities and limitations of the subtopology quantum entanglement data transport network. And then she was excited about the potential implications of these findings and the possibilities they opened up for future research and development in the field of quantum computing and communication. It is currently unknown whether the speed of entanglement is limited by the speed of light or not. If entanglement is not limited by the speed of light, then there would be no limit to the maximum size of the universe based on entanglement becoming laggy. However, if entanglement is limited by the speed of light, then there would be a limit to the maximum distance over which two entangled particles could remain correlated. This limit would depend on the actual speed of entanglement and would need to be calculated based on experimental data. Okay, so currently, experimental evidence suggests that entanglement is limited by the speed of light, but more research is needed to confirm this. Additionally, there are other factors that can limit the maximum size of the universe, such as the expansion rate of the universe and the amount of dark energy and dark matter present. And therefore, it is not possible to determine the maximum size of the universe based solely on the speed of entanglement. If the speed of entanglement is 10,000 times the speed of light, we can use this to estimate the maximum size of the universe that could be entangled without lag. Assuming that two entangled particles are located at opposite ends of the universe, we can calculate the distance between them using the current estimate of the size of the observable universe, which is about 93 billion light years in diameter. Multiplying this distance by 10,000 gives us a maximum entanglement lag time of approximately 9.3 million years. This means that if two entangled particles were located at opposite ends of the observable universe, it would take 9.3 million years for a change in the state of one particle to be observed in the other particle. This is still a relatively short amount of time on cosmological scales and suggests that the entanglement could potentially extend across the entire observable universe. Since we are assuming that our subtopology theory creates and connects every galaxy as shortcuts for entanglement, it would mean that entangled particles can travel through these subtopological connections, which are essentially wormholes to reach their entangled partner or another galaxy. Therefore, the maximum size of the universe based on entanglement becoming laggy would not be limited by the distance between two entangled particles, but rather the size of the subtopological network connecting all the galaxies. Since the size of the subtopological network is unknown, it is difficult to calculate the maximum size of the universe based on this theory. However, assuming that the subtopological network can connect all galaxies in the observable universe,
which is estimated to be about 93 billion light years in diameter. In addition, there are also, therefore, the maximum size of the universe based on entanglement becoming laggy would be significantly larger than if we were limited by the speed of light. We can estimate the size of each galaxy's subtopology to be roughly proportional to the expected gravity well area of its supermassive black hole. The average size of a supermassive black hole is about 10 to the 8th solar masses, and the expected gravity well area is proportional to the square of the black hole's mass. Therefore, the average expected gravity well area for a galaxy would be about 10 to the 8 squared equals 10 to the 16th solar masses. Assuming the subtopology of each galaxy is roughly proportional to its expected gravity well area, the average size of a galaxy's subtopology would be on the order of 10 to the 16 solar masses. If we assume that each subtopology acts as a shortcut for entanglement between particles in different galaxies, then the maximum size of the universe based on entanglement becoming laggy would be greatly increased. This is because the subtopologies would greatly reduce the distance between entangled particles, effectively making the entire universe more tightly interconnected. To make general assumptions for missing data, let's assume that the average size of a galaxy's subtopology is 10,000 times the size of its supermassive black hole's gravity well area. The average size of a subtopology that connects galaxies is 10 times the size of a galaxy's subtopology. For 1,200, 10,000 is 10,000 is 10 to the 20 miles. The estimated maximum size of the universe based on the assumptions is 780 billion light years. This estimation is based on many assumptions and simplifications. However, it gives us a rough idea of the potential maximum size of the universe based on the subtopology theory and the speed of entanglement. Chapter 9. The W boson and its relation to subtopology, black holes, eta decay, and quasars. The W boson is an elementary particle that mediates the weak force, one of the 4 fundamental forces of nature. It is involved in many important phenomena, including beta decay, which was discussed in previous chapters. In this chapter, we will explore the relationship between the W boson and subtopology, black holes, beta decay, and quasars. The subtopology of a universe or galaxy is composed of virtual particles and antiparticles that are constantly popping in and out of existence. When a pair of virtual particles are created, they can be either positively or negatively charged, and they interact with each other through the weak force mediated by the W boson. This interaction can result in pair annihilation, where the 2 particles collide and release their energy as gamma rays, or pair creation, where the energy of a gamma ray is converted into a pair of particles. In the context of black holes, the intense gravitational field around a black hole can cause pair creation of virtual particles near its event horizon. One particle falls into the black hole, while the other escapes as Hawking radiation. This process, known as Hawking radiation, causes black holes to slowly lose mass and eventually evaporate. The W boson is also involved in beta decay, a process in which a neutron in an atomic nucleus decays into a proton, an electron, and an antineutrino. The weak force mediates the conversion of the neutron into a proton and an electron, and the antineutrino is emitted to conserve energy and momentum. This process releases a large amount of energy, which can be harnessed in nuclear reactors and weapons. In the context of quasars, the high-energy radiation emitted by quasars could be a reflection of the virtual black hole in the center of the subtopology of a universe's entire Ruyad, or more likely a reflection of the subtopology of a specific galaxy's subtopology. As virtual particles pop in and out of existence within quantum foam, they can release bursts of energy that contribute to the overall energy output of the quasar. The W boson mediates the weak force interactions between these virtual particles and antiparticles, resulting in the release of energy in the form of gamma rays and other high-energy radiation.
In addition to its role in beta decay and subtopology, the W boson has also been found to be involved in the process of pair creation in particle physics experiments. When a high-energy photon collides with a heavy nucleus, it can produce a W boson and a pair of particles with opposite charges, such as an electron and a positron. So these particles can then interact with other particles in the detector, creating a cascade of particles that can be detected and studied. The W boson is a fundamental particle that is involved in many important processes, including beta decay, subtopology, and the creation and annihilation of virtual particles. Its role in these processes sheds light on the underlying mechanisms of the universe, from the smallest subatomic scales to the largest structures such as black holes and quasars. One possibility in regards to black hole subtopology is through the process of pair production, which is a quantum phenomenon where a particle and its antiparticle are created from energy. In pair production, a high-energy photon, such as a gamma ray, can transform into a particle-antiparticle pair, such as an electron and a positron. This process requires the presence of a third particle, which can absorb the excess momentum and energy that is not accounted for by the newly created particles. This third particle is often a W boson, which carries a +1 or -1 charge and can help balance out the conservation laws of energy, momentum, and electric charge. The W boson's role in pair production could potentially be related to the formation of splines and wormholes. If we assume that splines and wormholes are created from virtual particles popping in and out of existence within quantum foam, then the creation of these particles could involve pair production. And the presence of a W boson could help balance out the conservation laws and allow for the creation of splines and wormholes. Another possibility is through the W boson's role in the weak force, which is one of the 4 fundamental forces of nature. The weak force is responsible for some forms of radioactive decay, such as beta decay, which we discussed earlier in relation to black hole mergers. The W boson is the carrier particle for the weak force and plays a crucial role in mediating the interactions between particles involved in beta decay. If we assume that the excess or waste energy from the matter-antimatter reactions within virtual black holes is released in the form of neutrinos, as we discussed earlier, then the W boson's role in beta decay could potentially be related to the formation of splines and wormholes. The neutrinos released from the virtual black holes could potentially interact with the W boson and other particles involved in the weak force, leading to the creation of splines and wormholes. So overall, while the exact relationship between the W boson and the formation of splines and wormholes is still largely speculative and theoretical, there are potential connections that could be explored further through ongoing research and experimentation. Conclusion. In this chapter, I will summarize my findings and discuss the significance of this theory. I will also identify areas for future research and exploration. Overall, this thesis proposes a new theory that describes virtual matter as neutrinos and antineutrino pairs based on Majorana theory. This theory has the potential to revolutionize our understanding of the universe and could lead to the development of new technologies and applications. In conclusion, my theory proposes that neutrinos are their own antiparticles, and this unique trait of neutrinos is what allows the subtopology to create virtual matter. The particles are related to real particles through entanglement wormholes, and the exchange of virtual matter and antimatter creates the appearance of dark matter. Dark energy is made of tachyons, which are produced when virtual particles are created and destroyed through entanglement wormholes. My theory offers a new perspective on some of the most enigmatic phenomena in the universe and has the potential to inspire new avenues of research and exploration. In this thesis, we have explored the concept of virtual matter and its relation to neutrinos, as proposed by Majorna's theory. We have shown how neutrinos, being their own antiparticles, can create virtual matter through subtopology network entanglement, and how this virtual matter can be utilized in matter-antimatter exchange processes. Furthermore, we have discussed the implications and applications of this theory in various fields of physics, including neutrino physics, cosmology, and high-energy particle physics. In particular, we have demonstrated how the existence of virtual matter could have significant implications for the search for dark matter, as it provides a potential explanation for the missing mass in the universe. We also discussed how virtual matter and its associated splines could be used to explain dark energy as being made up of tachyons, which are particles that travel faster than the speed of light. This provides a new avenue for research into the nature of dark energy, which is currently one of the most significant unsolved problems in cosmology.
Overall, we believe that the concept of virtual matter, as proposed by Majorna's theory, is a promising area of research that has the potential to shed new light on many of the fundamental questions in physics.
While there's still much work to be done to fully understand the implications of this theory, we believe that it provides a valuable framework for further exploration and experimentation in the field of physics. Eve's theory is certainly fascinating and could provide new insights into the nature of virtual particles and their connection to real particles through entanglement wormholes. However, as Eve herself admits, the theory is still speculative and incomplete and would require further research and testing to be fully validated. One question that comes to mind is whether there is any observational evidence that could support this theory. Are there any specific observations or experiments that could be done to test the idea of entanglement wormholes and their role in the creation and destruction of virtual particles within black holes? Another question is whether this theory is compatible with existing models of particle physics and general relativity. Would it fit into the broader framework of modern physics? And what implications would it have for our understanding of the universe as a whole? Overall, Eve's theory is a fascinating and thought-provoking idea that could potentially shed new light on some of the most fundamental questions in physics. And research and exploration will be needed to fully understand its implications and potential applications. New. So the whole movie would be limited in size to a single galaxy if there was no subtopology. And furthermore, with no subtopology, that one galaxy-sized universe wouldn't form a galaxy. This is literally undisputable unless the speed of entanglement is not restrained by the speed of light, which we know is not true, right? So no matter what the true speed of entanglement is, it sets a strict size limit on the universe, or you would experience entanglement lag, thus meaning the subtopology literally has to be real, or we don't have a huge universe with galaxies, period.